White, 7th edition. As we described before, many fluids problems do not involve motion. They conserve the pressure distribution in a static fluid and its effect on solid surface and on floating and submerged bodies. In some problems, we maybe have, let me write a hydrostatic pressure in gases. In gases, as you know, the condition is different. Gases are compressible with density nearly proportional to pressure. Thus, density must be considered as a variable in the equation dP on dz equals to minus rho g. If the integration carries over large pressure change, it is sufficiently accurate to use the perfect gas law. So if we have a relation to the gas state, in some cases we have perfect gas, which a relation P equals to rho RT. So the relation will be different, as below we have dP on dz dP on dz equals to, we can calculate rho equals to P on RT. R is the standard gas constant. We can replacement with this relation minus P on RT, it is density multiplied to G. So with the simplification, dP on P equals to minus G dz on RT. In this case, we can have between 2.1 to 2.2 dP on dz equals to minus G dz on RT. This relation is the relation of hydrostatic condition for gases. The integral over Z required an assumption that the temperature variation, one common approximation, is the isothermal atmosphere where T equals to T0. So in this case, if G is constant, we consume, and also R is a constant, we can write, in this case with LMP2, let me write from here, this integration dP on P equals to minus G on R integration dz on T. If we have a function of T on Z, we can calculate this relation, but in the case of hydrostatic, we assume that T is constant equals to T0, T ambient. Isothermal atmosphere, atmosphere condition. So we can write L and P2 on P1 minus G on R integration with 1 to 2 dz on T0. So minus G R T0 Z2 minus Z1. This is the relation for isothermal condition for pressure. We can write also in exponential for that P2 equals to P1 exponential of Z1 minus Z2 on RT0. The quantity in brackets is dimensionless. Let me show in the next page. The quantity in the brackets, the relation was about the pressure in the gaseous fluid. We had this relation P, let me write with blue for example, P2 equals to P1 exponential, the bracket expression is G multiplied to Z1 minus Z2, Z2 minus Z1, R T0. So the bracket is a non-dimensional number, quantity or number. Is a fair approximation for Earth, but actually the Earth's mean atmosphere temperature drops off nearly linearly with Z up to the altitude, and in the case of the increasing the altitude of the problem, we have the relation for T as T equals to T0 minus BZ. Here T0 is sea level temperature and beta is the lapse rate, both of which vary somewhat from day to day. So it is the sea level temperature and it is the lapse rate. In the standard atmosphere, we have the values, we have some quantities for lapse rate and also sea level temperature. In the sea level standard atmosphere, we can write standard atmosphere T0 equals to 518.69 Rankine and equals to 288 Kelvin equals to 50 degrees centigrade Celsius, and the lapse rate equals to, in the British Rankine on foot, and in SI B equals to on Kelvin on net. This lower portion of the atmosphere is called troposphere. introducing the equation, this equation to the integration 4, we can obtain this relation dP on dz equals to, we had this relation for temperature minus G, we had P all equals to rho G T, and rho equals to P on rho G. Let me write again. Minus P on rho T GT, where T equals to T0 minus BZ dP on P equals to dz on G T0 minus BZ. We can integrate this relation. We can obtain P equals to T0 on T0 G on RB and for the density we can write rho equals to rho 0 1 minus BZ or T0 minus 1. This is a relation for the condition that the elevation level of the problems change strongly, but this effect on the temperature and consequently on the specific weight. We can also have another relation for temperature in the function of z and integration with this form. The main relation is the relation of hydrostatic equals to minus gamma. The next section in this chapter is application of the previous hydrostatic relation to manometry. Application to manometry. For the hydrostatic formula, we had this relation. A change in elevation Z2 minus Z1 of a liquid is equivalent to change in pressure with integration between 2.1 and 0.2. We can obtain the relation as below. P2 minus P1 on gamma equals to Z1 minus Z2. This is the relation for the hydrostatic liquids. Thus, a static column of one or more liquids or gases can be used to measure pressure differences between 2 points. Such a device is called a manometer. If multiple fluids are used, we must change the density in formula as we move from one fluid to another. This figure shows the use of the formula with the column of multiple fluids. Consider this picture. The pressure change through each fluid is calculated separately. If we wish to know the total change P5 to P5, this is a minus P1. Let me write. P5 is at the altitude of Z1, Z5, and P1 is in the pressure at the altitude Z1. We can write the successive change to P5 minus P1 as this formula. P5 minus P1, we have various pressure here, P4, P3 and P2. So we can write P5 example minus P4 plus P4 minus P3 plus P3 minus P2 plus P2 minus P1 equals to, for example in this case, Z2 minus Z1 this is P5 minus P1. And for the Z, we can also write this expression as Z5 minus Z1 equals to Z5 minus Z4 plus Z4 minus Z3 plus Z3 minus Z2 plus Z2 minus Z1. So with the replacement to the hydrostatics formula for the liquid or multiple liquids, we can write this expression P, for example, between P 18.1 and 5. We can write P5 minus P1 on gamma equals to on minus gamma equals to Z5 minus Z1, which is equals to this expression. For the various liquids with different density, we have this relation to n comma I Z n Zn minus Zn minus 1. For example, in this picture, we can calculate the pressure as this formula. We have P5 minus P1, the first liquid, for example, gamma 0, for P1 Z2 minus Z1 minus gamma 2 Z3 minus Z2 minus gamma 3 Z4 minus Z3 minus gamma 4 Z5 minus Z4. This is the relation for the manometer. No additional simplification is possible on the right hand side because of the different densities. Notice that we have placed the fluid in order from the lightest on top of the heaviest at bottom. It is the only stable configuration. If we attempt to layer them in any other manner, the fluid will overturn and seek the stable arrangement. Pressure increase downward is calculated as the formula in this page. So we can write pressure increase downward in this picture can be calculated as this relation. P5 equals to P1 plus gamma 0 Z2 minus Z1 plus gamma 1. In this case, gamma of this oil, this water, we can write water Z2 minus Z3 minus Z2 the magnitude plus gamma glycerin, the difference between glycerin and its top. We want to calculate this point pressure, which is Z4 minus Z3 plus gamma M multiply to Z4 Z5 minus Z4 in this point. And if we had the other point, we can also continue the relation. This is the pressure increase downward P5, and as a relation of the specific weights and the altitude of the various fluid in the column of the flow, total flow. That is, keep adding on pressure increment as you move down through the layer flow. The different application is a manometer, which involves both up and down calculation. The application of manometers. Consider this picture for an example for a manometer. This figure shows a simple U-tube open manometer that measures the gauge pressure PA relative to the atmosphere pressure PA lowercase. These two pressure open to the air and the gauge A pressure. This manometer calculate P, measure the P gauge, which is the P A minus P pressure of atmosphere. The chamber fluid has the pressure. The chamber fluid here has a density of ρ1, is separated from the atmosphere by a second heavier fluid ρ2, heavier fluid. Perhaps because fluid A is corrosive, or more likely because a heavier fluid ρ2 will keep Z2 small and the open tube can be shorter. We first apply the hydrostatic formula of the hydrostatic relation from A down to Z1. Note that we can then go down to the bottom of the U-tube and back up on the right side to Z1, and the pressure will be the same, P equals to P1. Thus we can jump across and then up to level Z2. So in this, we should go from point A to point end of the chamber fluid and continue to the Z2, which is the difference between this. We have also this relation PA minus P equals to sigma gamma I minus Zn minus 1. We can write P R minus P atmosphere equals to, the first is the fluid in the chamber with the gamma equals to rho 1 G multiplied to the ZA minus Z1. Actually Z2 is Z1. Z1 minus minus here. Z1 minus ZA minus rho 2G. Z2 in this condition is Z2 minus Z1 and plus, so PA equals to P atmosphere. If we apply the minus in this relation, we can write that plus rho 1 G Z A minus 1 Z1 minus rho 2 G Z2 minus Z1. So this is a manometer pressure application of the hydrostatic relation, which can give the gauge pressure between a reservoir and from to the atmosphere. Another physical vision that we can draw across at section 1, that is a continuous length of same fluid concept is 2 equals elevation. The hydrostatic relation requires the equality as a form of Pascal law. Any 2 points of the same elevation in a continuous mass of the soap, we can write the Pascal law for manometer in the next page. Said that any 2 points at the same elevation in a continuous mass of the same static fluid mass of the same static fluid will be at the same pressure. For example, consider this tube. If we had a liquid here, the pressure in the, for example, this elevation is P1, P1, P2, P3, P4, P5. This is a PA and also PA. It said that any 2 points at the same elevation in a continuous mass of the same static fluid will be at the same pressure. With all pressure P1 equals to P2, P3, P4, P5. Another example of the manometry application is the figure 10. Illustrates a multiple fluid manometer problem for finding the difference in pressure between two chambers. So consider the example for the another manometer application. This is in this type of problems, you should first start from point A to point B and write the pressure between two values, any values altitude. In this case, we start with PA minus P1 plus. For this two elevation, we have P2 minus P1. Because we goes from this point to this point, we should write P1 minus P2 plus, we write with green, and next P2 minus P3 in this point, and plus P3 minus PB. This is the left hand side of the hydrostatic relation equals to, now we write the right hand side of the hydrostatic relation, which was TP TP on TZ equals to minus gamma. So minus gamma A, difference between two altitude, which is Z2 minus ZA minus Z1 minus gamma 2 Z1 minus Z2 minus gamma 3 this fluid Z B minus, excuse me, Z. We always goes in same direction with P or Z. Z 3 minus Z B. So we have a relation to calculate the desired pressure. For example, gauge pressure on any point pressure in this manometer. The intermediate pressure P1, P2 and P3 can be cancelled during the calculation. It looks complicated, but really it is merely sequential. One start at A goes down to 1 and to reach to the point B as we described before. It is the end of this video. In the next video, we are going to talk about the hydrostatic force on the plane surface.